So we've got our oil summary page in our workbook here. I quite like these summary pages because they capture what we've covered in several lessons onto one page. Now, of course, it's impossible to get all that level of detail in, but we can. It allows hopefully you to see how the lessons link together, and they're really good place to start your revision. These summaries. So starting at the very beginning, fractional distillation. So the story of oil, if you like, started with saying we have crude oil at the bottom of the ocean, and crude oil is a mixture. It's a mixture. It's a substance that's made up of many different fractions, all mixed together. So they're not joined, just mixed. And the fractions are, if you remember, bitumen, which is road tar, roofing tar, fuel oil, kerosene, diesel, petrol, and natural gases, all mixed in together. So before we can use it, before we can fill a car tank with petrol, we have to separate that mixture. Now, fractional distillation separates the mixture, separates the crude oil. That's its job. So many times I ask students what crude oil do, and what fractional distillation does, and they can't tell me. So it separates the crude oil mixture. Now, just for the sake of this summary here, let's just assume crude oil, okay, coming out of the bottom of the North Sea, out of an oil rig, it comes down a pipeline. Okay, let's just assume the crude oil is a mixture of just two fractions, just to make it easy. Okay, let's say it's a mixture of petrol, because I think we can all understand what petrol is. We can picture petrol. Okay, we can picture petrol. Petrol is a flammable substance to make cars go. And bitumen, road tar. So the tar they put on the road. Okay, because you can all picture bitumen, I think, road tar. Okay, so crude oil, let's just say it's a mixture of those two things. Now, you can't put that crude oil in the petrol tank because it will gum up the car. We have to separate them. Okay, so what we do is we separate them using fractional distillation. Now, the first part of fractional distillation is to heat that mixture to boiling point. So this is a liquid here. Okay, and what happens here is it is heated and boiled. Okay, so what comes out here, okay, is now a gas. It's petrol and bitumen gas. That then gets put into a huge tower, okay? And this tower is a cooling tower. So in this tower now, these vapours cool down. Are we happy with that? Now, so we've got hot gases here, just where that pen is now, they're hot gases. Now, hot gases rise. Now, you all know this. You may not think you know it, but you know it, because if there's a Bunsen burner on the desk in front of you, okay, you know, your brain just knows not to put your hand above the lit flame, because you know it's going to get burnt quite badly, okay? You know you can put your hand to the side of it or beneath it, okay? And the reason that it doesn't get burnt quite badly is because hot gases rise up. The hot gases and the Bunsen flame rise up. And it's the same with this petrol and bitumen. They rise here, and this is a cooling tower, remember? A cooling tower. Okay, cooling tower. So as they rise here, they start to cool down. So if I say it's about 400 degrees when it comes out of here, so as these bitumen and petrol gas at 400 degrees come into this tower, they're cooling down. So what's 400 degrees? So as they come into the tower, it goes 390, and now they're rising up because they're hot gases. They rise 380, 370, 360. Now, bitumen's boiling point is roughly about 360 degrees. You don't need to learn that. Okay, you just need to know it's the highest boiling point fraction. So 360 degrees, bitumen turns back to a liquid because it's cooling and it's got to its boiling point. Now, hot liquids don't rise, hot liquids fall. So if you could put a camera in the tower here, you would see it raining bitumen, raining road tar. And as it falls, as it rains, it falls out the bottom here. So out here at the bottom of the tower, we get liquid bitumen. Okay, but the petrol gas is still a gas, and it still rises, and it cools. So it was 300, 250, 200, 150, 100. Now, around about 80 degrees, petrol turns back into a liquid as well. So just before it gets to 80 degrees, it goes through this hole in the tower. Now, above that hole, there is a lid. It's not joined, so the hot petrol gases can rise up, hit the lid, and then come sideways. And so when they get to about 80 degrees here, it starts raining petrol. And as it falls down, it hits that lid, so it can't go back down the hole, comes down the side, and then comes out here. So we get liquid petrol. So we've kind of got like a one-way trap in that cooling tower. And that is how, this process is called fractional distillation, and that is how crude oil is separated. Now, of those two, bitumen has a long chain, okay? Petrol has a short chain. And that dictates the characteristics of those chain molecules, the chemistry of those molecules, if you like. The long chain molecules have high boiling points. The longer the chain, the higher the boiling point, the shorter the chain, the lower the boiling point. And so actually, crude oil has more than 2 fractions. It has 5 or 6 fractions. So we actually have 5 or 6 one-way traps in this tower, and that's how it separates them. But the shorter the chain, the lower the boiling point. Short chain boiling point is low. Flammability. Bitumen is not flammable. You do not see the roads bursting into flames. Not flammable. Whereas petrol, hopefully you've never seen petrol bursting into flames, but we have to be really careful at petrol stations because it is highly flammable, almost explosive in its flammability. And not flammable, so very flammable. Short chain, very flammable. You need to know the trends in carbon chain length, okay, and these characteristics. Viscosity is how thick the liquid is. Well, petrol's not very viscous because it flows out of the petrol pump into the tank. Okay, so the short chain is not viscous, whereas tar is so viscous, it is a solid. Okay, so very viscous. Okay, the longer the chain, the thicker it gets. Now of those 2 fractions, petrol extremely useful, very flammable, but the longer the chain, the less useful they get. So some of these long chain molecules we don't have a lot of use for, but what if we could cut those chains up? Okay, and that process is called cracking. Okay, cracking is shortening a hydrocarbon chain. If we shorten the chain, it makes it more flammable. Short chain, very flammable. Shortening the hydrocarbon, we're squeezing that in there, the hydrocarbon chain. Now, the apparatus. It's going to be a struggle to fit it into here, and these summary diagrams aren't brilliant because there isn't sometimes quite enough room. But when we did this in the lab, we had a boiling tube here, and we collected the gas given off over water. So we had a trough of water here, okay, and we had a test tube on top of it, like so. Okay, now in this tube we heated we use brick catalyst, broken up brick, but you can use broken pot as well. That was a brick catalyst. Okay, and the long chain hydrocarbon we used, we put in some Roxawool, so some Roxawool, some mineral, that just keeps that just soaked up the paraffin. Okay, we used paraffin, that was the long chain alkane, that was the long chain. They're not flammable. Okay, but if we can break that chain up, we can make it into more petrol type like molecules, and that's very flammable. An example equation, there's lots of different equations for cracking. So C10, let's just pick 10 carbons. That would have 22 hydrogens if it's an alkane. Okay, normally we do equations going horizontally, don't we? I haven't got room here, so I'm just doing it vertically. Okay, so if we take that long chain hydrocarbon and we crack it, we break that chain, it becomes C8, H18. Now the difference there is 2 carbons, 10 minus 8 is 2, so it's going to be plus C2. And the difference here is from 22 and 18 hydrogens is 4 hydrogens, so that's C2H4. 2 reasons for cracking. 1, makes a more flammable alkane. Okay, so we start with this here, not flammable, because it's long, and we make this here more flammable because it's shorter. That's 1, more flammable. And 2, it makes the raw material for polymerization. Now, polymerization is the process of making plastic. Okay, so this molecule here is an alkene. It's not plastic, it's the raw material for making plastic, and that's called polymerization. Okay? Right, alkanes and alkenes. If you are a separate scientist, you need to know the first members of the alkane and the alkene family. So the first members of the alkane family were methane, CH4, so that's carbon with 4 hydrogens. Okay, propane, C2, C2H6. Looks like it's all single bonds. These are all found in crude oil, C2H6. Okay, and C3 is the third one, that's propane. And you need to know these names if you're a triple scientist as well. So that's propane, ethane, and methane. So meth is 1. We can put that up here, can we? So meth equals 1 carbon, eth equals 2 carbons, prop equals 3 carbons, and bute equals 4 carbons. You only need to know that for triple award science. Okay, so if we look at the alkenes, first one is ethene, so eth is 2 carbons, so that's C2H4, C2H4. And the thing to remember here is every carbon can only form 4 bonds, so 1 bond, 2 bonds, 3 bonds, 4 bonds. Really important when we do propene. Propene is the next one, propene, C3H6. So it's got 1 double bond, doesn't matter where you put it, but what does matter is how many bonds we put around these carbons now. So that's got 1 bond already, this carbon, so 2, 3, 4, fill those with hydrogen. This carbon in the middle, it's got 1 bond, 2 bonds, 3 bonds, needs 1 extra, 4. This carbon on the end, it's got 2 bonds, 1 bond, 2 bonds, needs 2 more, 1, 2, there's propene. Right, so alkanes have single carbon bonds. They are less reactive, and tested with bromine water is the bromine water stays orange. And they are saturated, whereas alkenes are exactly the opposite. They have a double carbon bond, they are more reactive. Tested bromine water is it decolorizes the bromine water, and they are unsaturated. Right, bottom row, we all need to know this, double award and triple award. Okay, we burn most hydrocarbons. The products of complete combustion of hydrocarbon are carbon dioxide and water. Incomplete combustion, names and products the products are, there's 2 products of incomplete combustion we need to know about. One is carbon, solid, okay, which we call soot. And 2, okay, is carbon monoxide. And that is a gas and it's toxic. And its formula is CO. Okay, so formula of carbon was just C. Okay, why are they formed? Burning without enough oxygen. Think about it, carbon dioxide, when we have complete combustion, is CO2, carbon with 2 oxygens. Carbon monoxide, carbon with 1 oxygen, carbon with no oxygen is just carbon. Okay, so this is burning without enough oxygen. We get 2 products, carbon soot and carbon monoxide. Why is carbon monoxide toxic? Okay, breathe it in and it joins to hemoglobin. Hemoglobin is the red blood cells. Stopping oxygen and carbon dioxide travelling around the body. Normally we breathe in oxygen, hemoglobin takes it to our cells where it's needed. It hops off the hemoglobin there and carbon dioxide joins, and then your bloodstream takes that back to your lungs and you breathe it out. Okay, carbon monoxide joins that hemoglobin and doesn't let go. Last bit, advantages and disadvantages of hydrogen as a fuel. Well, there's loads, aren't there? Okay, so hydrogen as a fuel. Main advantage, product is water, okay? Environmentally harmless. Doesn't lead to global warming, okay? Doesn't lead to global warming. Or acid rain. Okay, that's the single biggest advantage. Okay, so that's our advantage. We can make lots of hydrogen from the electrolysis of water. There we go, so that's another advantage. Can be made from electrolysis. Disadvantages, loads. So disadvantages. 1, hydrogen is expensive. 2, no hydrogen infrastructure. Okay, you can have a fuel cell car, okay, but you ain't got anywhere to top it up with fuel, have you? Infrastructure, so you can't drive it anywhere. You can't. There's no hydrogen filling station down the road. Okay. 3. Hydrogen is dangerous. It's explosive. Lots and lots of different reasons. And there's, advantages that fuel cells are quite efficient. But go back in your book for more. We just need to learn a couple of advantages, a couple of disadvantages.